Hey guys, so welcome back, and today we're going to be introduced to science, physics, and scientific investigation via scientific method. Now you might ask yourself, what is science? Well, believe it or not, science is not just a subject in school. It has real-world application. It is used to create new technologies to improve our lives. And it is simple. After all, science comes from the Latin word scientia, which means knowledge. So I'm going to ask you what you think sentient means. Science is a process that uses observation and investigation to gain knowledge about events in nature. So nature follows a set of rules. We know this. Many rules, such as those concerning how the human body works, are complex. Other rules, such as the fact that the Earth rotates every 24 hours, are simpler. When you study these natural patterns, you are doing science. You are being a scientist. Our objective for today is to be introduced to science, to be introduced to physics, know what physics is, and to be introduced to the scientific method. Now, we are going to learn ourselves, our world, and our universe through science, through physics, from the subatomic level all the way to the astronomical level. Now, science explains nature. Many different branches of science. There's the laws, such as studying, living things, from the macro level, like this frog here, all the way to the micro level, talking about macromolecules and cells. You still have to use scientific investigation and scientific methods, tools, and technologies to study. And other branches of science include the earth sciences, right? You're studying the earth, you're studying ocean currents, tectonic plates, meteorology, geology, etc. So in earth sciences, you learn more about the earth, how the earth functions. Now, other sciences are the physical sciences, which deal with matter and energy. Examples are chemistry. Now, in this course, our main focus is the physical sciences. Sometimes, however, a scientific study will overlap with other categories. As such, we will cross in the realm of other sciences at times. So we are going to blur the lines, and at times we're going to step a little bit into biology, or a little bit into chemistry, or a little bit into the earth sciences, just as geology. Now, for example, a scientist might study the motion of the human to better build artificial limbs. Now, is this scientist studying energy and matter, or how to operate? Is he using physical sciences, or is he using life sciences? That scientist is using both. And so that's what's going to occur in my classroom. Now I'll talk more about physics. So those that their main focus is physics, they become physicists. They're known as physicists. And physicists want to know how things work. They observe nature and figure out the rules or laws that govern its operation. And this basic curiosity is at the heart of all advances made in physics over the centuries. Now, physics is a study of the fundamental laws of nature. And the major categories of physics is force and motion, energy, momentum, electricity and magnetism, waves and particles, entropy and thermodynamics, and then you have atomic physics and nuclear physics and modern physics. These are all topics that we are going to learn about throughout this year. Now, the fundamental laws that describe these different areas of physics are usually expressed in terms of mathematical equations. It is the most basic of the sciences, and its laws, the equations that have come up in all the other sciences, and help to explain what is observed in those sciences. Now, these fundamental laws, as I said, are usually expressed in the terms of mathematical equations. Yes, you will have to use mathematics in physics. And as soon as an observation becomes a mathematical equation, you now create a theory, right? And theories can be used for ongoing investigations, right? You now have an equation. You can make new observations, set up new experiments, and determine, well, does this mathematical equation, does this theory, if I test again and again, does it accurately predict what I am observing. If it does, then your observations are supporting that theory. If it doesn't, then you are rejecting that theory, and that theory needs to be revised. Now, before we move any further, I want to give you just a short background on the advantages of physics and becoming competent or great skills in physics. So you might be thinking where I might work as a physicist. Well, a strong physics background can prepare you for almost any occupation that involves science. Or engineers said that the rules of physics, the science of physics, supports all the other sciences. So being strong in physics would allow you to be prepared or go into occupations that involve transportation design or construction, technology development, civil and military construction, and occupations being an electrician, a welder, a plumber, a technician. Now, science is the accumulation of knowledge, right? Science, the laws and theories that are published aren't going to be 100% accurate. And so I don't want y'all to have that misconception that science is true and that knowledge is complete and that we never know. There's still a lot to be learned. And every time you learn new information, that creates more questions. So we're never going to run out of questions. Investigation will be necessary to discover the next level, the next layer of explanation. So no amount of observation or investigation can ever prove a theory is absolutely 100% correct all of the time. Although a single experiment prove any theory. For example, in the late 18th century, scientists used to believe that heat was a fluid that had very, very little mass. Well, now we know better through scientific investigation, right? We now know that heat is not a fluid at all. It's just kinetic energy at the atomic level. And that kinetic energy can be spread through convection or conduction or radiation. So, continuing scientific investigation proved an older theory incorrect, and that theory had to be revised. This is the scientific method, the investigation via scientific methods. So underlying all scientific investigations are the guiding principles of the scientific method. And these principles are statement of the problem, observation, where you collect data, hypothesis, proposed explanation, experimental testing, and in that experiment you test the data from the experiment, and then analyzing that data, you either accept or you reject your hypothesis. Now, investigations, you do them every day. Have you ever played a new video game without referring to the user's manual? I know I have. I have the manual. You push a button to see what happens, or you move to a new area to see what the effects are. As you make choices, you observe what happens on the screen and begin to rules of the game. Well, science is very similar, except we are trying to learn the rules of the real world, not the virtual world. So, in science, you have to be very systematic. Good science is good observation, so you have to record what it is that you see. So we're going to have an example of the scientific method. So I know that we're all very familiar with gravity. See objects fall all the time. Well, we're going to do an example of the scientific method trying to describe falling objects, how quickly they fall. So in this example, we will observe a falling object and attempt to predict the distance it will fall in time. So we're trying to determine the acceleration that that falling object experiences because of gravity. So the mathematics is ignored here in order just to provide the basic steps in the process. So we're not going to do a lot of math. I'm just going to show you how it's done. So statement of the problem. We need to be able to predict the time to fall for distance. That is our problem. We want to know how quickly does an object fall given a certain distance. So you have to measure the distance y, and then you have to record it with some type of stopwatch or more accurate keeping device. By stating the problem, we simply verbalize the need to know or to be able to predict some event. The problem might not be solvable, however. Not all problems are solvable, but it takes scientific investigation to do that. So, you set up a number of observations, or trials. So to address the problem, we organize the data into several trial observations. So we're going to drop the object from a higher height of known distance, and we're going to take the time that it takes to fall. And we're going to do more than one drop, right? I would say, rule of thumb, at least do 3 trials. Then at a smaller distance, we'll call y2, we'll run a number of trials. 1, 2, 3, recording the time for each drop. And then we have another observation, y3. Drop it again, 3 times, taking time each time. And now we have data, and we want to analyze that data. So you can create a table, right? You input your time observed and the distance that matches up with that, respectively. And using that data, you can create a graph using some type of program. This is Excel. All you gotta do is fit a trend line to that graph. This is analyzing the data, and tell that program to give you a mathematical equation. Now you have a theory describing the rate at which an object falls. And with this equation, you can test other observations and see whether or not your equation is accurate or inaccurate. So here's our equation. This is an incredibly small number right here, so we can ignore it. So now we have a hypothesis. Hypothesis is our mathematical equation technique to data. We note that the time of fall is proportional to the square of time, t squared. So remember, our equation was y equals 4.9 times x squared. X is time, y is distance, the vertical distance. So the equation looks a little bit different here. But our 4.9 is what we describe as a constant. We often represent constants with lowercase italic. So k equals 4.9 meters per second squared, our constant. And now we can use this equation to test. Right? The next step is, and for others, is to test the hypothesis. If time is given, right, we should be able to determine the distance that object fell. Or if distance is given, be able to determine how long it will take that object to fall from the top of the height to hit the ground. So each time the distance is predicted correctly, the theory is reinforced. Each time the time is predicted correctly, the theory is reinforced. In order for a theory to be accepted, it must be consistent and repeatable by others. So if anybody uses the equation, they have to be able to use it and predict accurately. Given enough time and enough scientific investigation, this hypothesis can become a theory. So it's all about your data or rejects your hypothesis. So each time you test it, if it supports your hypothesis, and your hypothesis continues. But if there's ever a single experiment that does not prove your hypothesis, right, you may need to revise it, look at it again. It's what Albert Einstein said, right? No amount of experimentation can ever be right. One single experiment can be wrong. This is the core of science. You can never prove anything to be absolutely 100% true. There might always be exceptions. So to review again, our scientific method is statement of the problem, observation, data collection, hypothesis, proposed explanation of your observation, experimental testing, and you collect data from that experiment. You analyze that data, and using that analysis, you conclude whether or not your hypothesis can be accepted or rejected. I hope you're having a good time.